coding and inference.
Thank you very much. So first of all, I want to put a shameless plug for the company here. I know there are a lot of students here, and I want to say we have a lot of internships, and our interns publish. So please take a look at our webpage and see if there's anything interesting. We do a lot of good work. Having said that, let's start with our topic. So today I want to talk a bit about kind of where things are going. A lot of the signal processing is moving to the cloud. And the big picture is that generally you have a signal, and then you have a cloud, which has computers and data. And you want to transmit the signal to the cloud and use all the auxiliary data and side information that the cloud has, and compute something about the signal. So you want to output a function, g of x and y. So this is a very general problem formulation. There are several questions here. You want to do some kind of information scalable processing and transmission. So for example, how to only transmit information that is required by G. So don't transmit superfluous information. The goals are efficient transmission, efficient computation, the interaction of transmission and computation. I'm not going to solve this whole problem today. As you can imagine, this is a huge area where people can do research, but I'm going to talk a bit more about specific cases. But it's a very widely applicable problem. You can think of augmented reality, remote medicine, surveillance, all sorts of authentication, all sorts of problems actually fit in this framework in processing in the cloud. So I'll give you some examples of where the problem has been examined already, even though we don't call it in that framework, but it fits that framework. Let's say that you have no auxiliary information, so there's nothing here, and the output of the function is just the signal itself. In that case, and if you're interested for the rate that you're going to use to transmit the signal, this is the standard compression. So there's a lot of work on rate distortion. If you don't want to have an exact copy of the output, there's rate distortion theory, standard compression techniques. This is a very well-studied problem. Another problem is when you have auxiliary side information, again, you want the output to be that same signal that you transmit, but you have auxiliary side information, which is similar signals to your signal, and you know that they're similar. This is also a very well-studied problem. It's called distributed source coding, or coding with side information. And there are several results from the information theory community, like Sleppy and Wolf coding, if you want lossless coding, Wiener Ziv, if you want to talk about rate distortion bounds and things like that. So these are, in some sense, solved problems. I wouldn't say they're fully solved, but in some sense, solved problems. There's always ongoing research in improving those. But today, I want to talk about a very different problem. The output that I want to compute is a function of the distance between two signals. Okay, so the auxiliary information will be some other signal, and I want to transmit my signal and compute the distance between those two. And what I'm going to use is a tool called Embeddings, and I'll describe more about embeddings. But one of the key questions is, why do I want to compute distances or functions of distances? And the reason is that distances are used everywhere. So inference, classification, clustering, detection, estimation. Distances are a key primitive in a very large number of signal, I would say most signal processing operations that we do. Okay? And together with distances, I can, by preserving distances or functions of distances, I can also preserve the geometry of the space. So I can preserve sometimes inner products and things like that, and I'll talk about it. Okay? So to motivate my discussion, I'll just give you a cloud-based signal retrieval problem. You have your smartphone, and you take a picture, and then you transmit it to the cloud. And the cloud has similar pictures and metadata about those pictures. And the goal is to find the picture that to find a similar picture to what you looked at, and get some data about that picture and return back what you're seeing. Okay, so this is a common problem in augmented reality. Compression is necessary because there's a lot of bandwidth going to the server, but the server doesn't really need to know the whole picture that you transmit. It just needs to know enough information to make the inference and tell you that this is the Golden Gate Bridge. Okay? So the question is, can we transmit? Do we need to transmit the whole signal? Of course, as I will argue, no. And can we reduce the rate? And as I will argue, the answer is yes. So let's see how these systems typically work. Usually you have a picture that you want to use to do the signal-based retrieval, the picture-based retrieval. And then there's a database. And from that picture, typically you extract descriptive features. So yesterday we talked, there was a very interesting talk about features in 3 dimensions, and they mentioned SIFT features and things like that. So these are the features that you extract. I'm not going to argue about which feature is best. I will leave that to the expert in this area. I'll just say that you have your feature set that you think is the best to describe your image. So you extract descriptive features, and you use those features to query your database. So you do the same thing in your database. You have the same features, and then you ask your database, find similar features. You know, there are several ways to do that, like support vector machines, nearest neighbors, all sorts of inference methods. But you find similar features, and from that you get an answer that, you know, this is a picture of the University of Maryland. Okay? So if we go back and see the pipeline, you have your picture, you have your feature extraction, you have your detection and classification, and then you have the result. Where should each stage happen? You could transmit the whole image, and then do the feature extraction at the server, and then do the detection and classification at the server, right? If you were to do that, you would compress the image and you'd reconstruct it at the server, right? But the feature extraction is not something that requires that big database at the server. It doesn't require the big processing power in the cloud. You can actually do it on your client. So you could do the feature extraction in your client and transmit your features, and then use your features to query your database at the server. So remember, the detection and the classification, as I've argued before, is using all these primitives about all the geometric primitives, so distance computation, kernel, inner product computation, and so on. So it's based on the geometry. So what we would like to do is follow that model, and I'll show you afterwards that actually does make sense if you compare it with the previous model. Follow that model and do a geometry preserving feature transmission. Okay? Okay, the tool we're going to use for that is geometry preserving embeddings. And most people here are familiar with embeddings, but I'll go over it really quickly. Generally, the embeddings are transformations that preserve distances. So you have a space that is high dimensional, expensive to work with, and what you do is you find the function and you go to an embedding space. And typically that space is either low dimensional or in some other way easier to work with. It might be binary and so on. And the main property of this function is that the distance between 2 signals is approximately equal to the distance between the embeddings of those 2 signals. And the most famous example is the Johnson-Lindenstrauss embedding. So there, what Johnson-Lindenstrauss showed is, well, they showed that you can create a linear transformation, or create a transformation that preserves the L2 distances between pairs of signals. And they actually showed that this is the exact statement of the Johnson-Lindenstrauss embedding property. They showed that you can preserve the distance within epsilon of the original distance using log p, where p is the number of points in your original space, using log p, order log p dimensions. And then there is this epsilon that decreases as 1 over square root of m. Okay, so if you want to have a better distance preservation, then you have to increase your measurements by this constant decreases as 1 over square root of m. Okay, and we know from all the work that has been done on that and the restricted isometry property and so on, that a probabilistic construction, so getting a linear map with randomly drawn entries, actually gives you with extremely high probability this guarantee. Now, this is a first step to solving my problem, but I want to transmit my features. So I could take the features, embed them to reduce dimensionality in a lower dimensional space, but I still need to quantize my features, right? I care about the bit rate. So this is tied to what Sinan and Alex were talking about yesterday. So I want to do quantization. Only here I don't care about necessarily about reconstruction on the other side. So let's do the obvious. Let's do the JL embedding and then do a scalar quantization. So every coefficient in the JL embedding, in the lower dimensional space, I will quantize with b bits per measurement. So my total rate, if I have an m-dimensional embedding, is b times m. Okay? If I increase b, and therefore I increase my rate by increasing b, I have less quantization error. If I decrease b and increase m, I have more quantization error, but I have less projection, Johnson-Lindenstrauss error, that epsilon. And specifically, we can actually show an embedding theorem. So there's a case of binary embeddings, which I won't go to when you quantize to 1 bit. But in the case of multi-bit embeddings, you can actually show that basically you preserve the Johnson-Lindenstrauss property, approximately. But you also have an additive error term, which has to do with your quantization. Okay? And the more bits you use, the smaller this term is, so the less the quantization distortion. The more measurements you use, the higher the space in which you project, the less the JL type distortion. So you have a trade-off here. And we can see that in practice by if we run some experiments. This is an experiment where I'm randomly drawing signals at different distances, and I'm embedding them, and then I'm computing their distance. So this is at a fixed dimension. So I'm projecting them to a fixed dimension, not a fixed rate. And then I'm quantizing to 2 bits, 4 bits, and 32 bits. 32 bits, you can essentially think of it as unquantized, right? It's extremely fine quantization. And you see that the signal distance is approximately, if you quantize to 32 bits, it's approximately proportional to the distance of the embedded signals. Okay? So you see this is a very thin ambiguity, whereas if I quantize to 2 bits, this is a very wide ambiguity. You have a lot of quantization error, okay? Which is what we expect and what the theory says. Now, what this comparison doesn't show, and it's not fair, is that if I use 256, let's say, dimensions, the 2-bit embedding uses 512 bits. The 4-bit embedding uses 1024 bits. The 32 bits embedding uses a lot of bits. I don't even want to calculate that, right? So to be fair, we actually need to do a comparison that takes the rate into account. So here I'm doing the same experiment, but I'm fixing now the rate to be 256 bits. So the 2-bit embedding will use 128 dimensional projection, whereas the 4-bit embedding will use half of that, 64 dimensional projection. And you see here that if we keep the rate fixed, which is what we care about, actually the 32-bit embedding doesn't look that good anymore. The 2-bit embedding is maybe a bit more ambiguous, roughly similar, and the 4-bit embedding still preserves that kind of tight, the small ambiguity. I mean, everywhere the ambiguity increases because I've also reduced the number of measurements, but in general, you see that now there's a trade-off that you need to explore. So schematically, if you want to see it pictorially, there is the error due to Johnson-Lindenstrauss embeddings, and then there's the error due to quantization. And as you change the number of bits per dimension, keeping the rate constant, because that's what we care about, one increases, the other decreases. Now, there are a lot of constants here, so this is just purely pictorial. This is not an exact thing that you can go and say, oh, this is my minimum, and therefore I can run that. There are a lot of constants, and you'll see in all these proofs, the constants are, they swipe them under the rug, and no constant is tied. Plus, this quantization, this Johnson-Lindenstrauss type error also depends on the distances of your signals, right? So you can't really optimize things other than experimentally, but there is a trade-off that you need to explore. Okay? Any questions so far?
Is it clear that you don't want to quantize and then embed?
I think it is clear because after you embed, you'll still need to quantize again because you need to transmit the embedding, right? Yeah. So you're just introducing another distortion before the final distortion. Okay, yeah.
How much does this depend on the sort of intrinsic dimensionality of your data that you're trying to?
So it depends on what's your signal model. If you have p points, it doesn't matter the dimensionality. If you actually try to look at manifold models or sparse signals and so on, then this log p changes to log of the Kolmogorov entropy of that set. So that changes with dimensionality. Okay? Okay, so the other thing that we need to think about is, I'm talking about inference. And when we're doing inference, I'll give an example with nearest neighbors. But generally, we care about preserving distances of points that are close to each other. We don't care that much about distances of points that are far. Let's say I have a signal and I want to find its nearest neighbors. And it's the same thing with support vector machines. What I'm going to do is I'm going to take the signal and draw a radius around it or expand the radius until I start finding nearest neighbors. So I care to preserve those distances as well. But as long as those signals stay far apart, I don't really care to know how far they are. And most inference methods really don't care about signals that are far. They only care about things that are in your local neighborhood. So the question is, can I reduce my bits by not really preserving this distance here, only preserving this distance here? Of course, and you know, going back to my original question, I didn't say that the output is a distance. I said that the output is a function of the distance. So I'd like to be able to compute more general functions. And the question is, can I do it? And of course, you know, I wouldn't be giving this talk if I didn't have an answer that was yes, right? So the answer, one part of the answer, there's a lot of work on that which I won't go through because of the time, but part of the answer is universal quantization, okay? So to understand universal quantization, I'll start with understanding scalar, regular scalar quantization and figuring out what we can learn from bits. So let's say we have 3-bit quantization intervals, so we have a real line and we want to quantize it with 3 bits. That means 8 quantization intervals, 2 to the 8. And let's say this is our point. So we want to see what each of those bits tells us about our point. So if you look at the most significant bit, this splits the line into 2 areas. This area versus this area. I'm going to do purple for things where my point is not and white for where my point is. So we know that my point is somewhere here. The second most significant bit, if we ignore the most significant bit, tells me that my point is either here or here. So it gives me a bit more local information, but it gives me also ambiguity about whether it's which side of the locality. And I use the most significant bit to disambiguate that part. Same thing with the third most significant bit. I'm either here, 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 or here, and then I'm using the other bits to disambiguate which part of the interval. But really, the local information is really in the least significant bits. Okay? So my question is, can I isolate this information in an intelligent way in the distance map and form the distance map? And the answer, of course, as I said, I wouldn't be giving a talk if the answer is no. The answer is yes. And the solution is to modify the quantizer. And in kind of, in hindsight, obvious way, just keep the least significant bits. So what I'm going to do is I'm going to do the standard Johnson-Lindenstrauss embedding. I will add dither, and that is both a proof tool and actually helps in a lot of properties here. And now I have control of the dither. And I will explicitly put a scalar here, which is essentially, I'm the quantization interval of the quantizer. So I can just move it in here in the scalar. Okay? So I'll use an IID Gaussian matrix. The dither will be IID uniform in the interval 0, 1, or actually 0 delta. And then I'll do the scaling and then do the scalar quantizer using this model. So I think Alex had this consistent reconstruction pictures. I'll have a similar picture here. Let's say I have a 2D space and I have a point here, and I take my first measurement. What you see here, Alex had basically everything would have been purple except for this area here. What you see here is that there's a lot of ambiguity in multiple points with one measurement. But then you take another measurement and you take another measurement. And as you take measurements, everything else kind of fills up. And if you were to do that, not in PowerPoint or Keynote, but in MATLAB, you would actually see that this is roughly uniform half purple color. This is white. And there's actually a gradient that slopes linearly, and I'll show you exactly how it slopes, going from here up to a point, and then things become uniform. Okay? So this is how the measurements behave. Can we analyze them mathematically? The answer is yes. We can actually show an embedding theorem. If we look at the 1-bit version of that, we can also do it for the multi-bit, but the 1-bit version, and we take the Hamming distance in the embedding space, this is within G of D, within delta of G of D, where G is given by this expression. Now, I have to say there are techniques to generate other Gs. I told you I wanted to have a more general G. We can't have the most general G, but there are techniques to generate other Gs, which I won't go to in detail today. But there is a G, and it's a messy expression, but it actually looks very nice. This is G plotted. What you'll see here is that there's basically a constant slope, and then it flattens out. Okay? And you can actually bound that, and not just bound it, actually approximate it very well with those bounds. It's bounded from above by 0.5. Remember, it's normalized Hamming distance. And it's bounded from above by this line here, which depends which depends on delta as 1 over delta. So as actually I reduce my delta, I reduce my quantization, so I make things more local, the slope increases. Okay? Now, given that I give you a signal, you get a signal, you want to form a distance estimate, the way you would work, I embed it, I transmit two signals, you compute them, you compute the Hamming distance, and you want to figure out their actual distance. What you would do is try to invert that curve. So let's say that the Hamming distance is 0.3. You go here and invert it, right? And that gives you a distance estimate. So basically, your distance estimate is G inverse of that curve. But then the question is, what is the ambiguity? And it turns out the ambiguity depends on the slope of that curve. So if you figure out that the Hamming distance of the embeddings is 0.5, you don't know really how far the signals are. You know just that they're farther than this. Okay? So what I've done is I've shrunk all the large dimensions to distance 0.5. All the large distances to distance 0.5. Okay, so I've really compressed my space in that sense. And I've eliminated all the information on those distances. Okay, so let's see how it works again with those in practice. So here's an example with two different bit rates, so high bit rate, low bit rate, and two different deltas, small delta, large delta. Okay, and you can see, of course, that as I increase delta, I preserve a smaller radius of distances. So the red curve actually preserves distances up to here. The blue curve preserves distances up to here. Okay, and what you can see is that the width of those curves changes. So the embedding guarantee, excuse me, the embedding guarantee is given in terms of the vertical direction of this and the number of bits. However, if I take two signals, I embed them and I transmit them to you, you will compute a Hamming distance. Okay, that Hamming distance, you want to go back to the curve and figure out the ambiguity in that direction. So remember, all the embedding guarantees in the literature are basically in this vertical direction. To convert it, you basically need to divide by the slope, which means that things that have higher slope at the same bit rate will actually give you a much tighter distance estimate. Things that have lower slope at the same bit rate will give you a more ambiguous distance estimate. You can see it very clearly here. It's a very tight distance estimate versus here where it's a very ambiguous distance estimate. Okay? What that means is that I have control. I can select my delta so that I preserve more distances but not as well. Or I can select delta to preserve a smaller radius of distances but much better. Right? And actually you can show that the radius to the ambiguity is constant given the bit rate. Okay? And then there is this flat region. So this is what I've been telling you about the slopes. There's small delta preserves smaller range, and larger delta preserves higher range. Now, another thing that is interesting is that I actually have an analytic expression that has no constants in there. So if I know the radius I want to preserve, I can set my delta. Okay, which is very important. There are no constants that we need to bound and tighten and screw this and that. The only thing that is loose in terms of constants is this width, but that doesn't affect very much my design. Okay. Okay, so this is good so far. There's one more thing that we can show in this example, in this particular embedding. We can show that it preserves what's called a kernel inner product. So kernels are a very commonly used tool in machine learning. And we can show that if you take the inner product between two embedded signals, it is actually 1/2 minus g of d. And this is approximately equal to e. Oh, there's a minus missing here. E to the minus some constant times distance squared. Okay, this is a very well-known radial basis kernel, the Gaussian radial basis kernel, which is very widely used in support vector machines. So, if you know what it is, then you understand this. If you don't know what it is, think of it as a way of computing inner products in a very high dimensional space using very few dimensions. Okay? Okay, so I've given you tons of theory and stuff like that. How does it work in practice? Let's start with a simple example of support vector machine classification. So we have we take Hog features from images, and there are 8 classes, car, person, wheelchair, stop sign, and so on. There are 8 classes. And then we try to do the embedding, query the database of similar signals, and use a linear support vector machine classifier and extract the actual what the image is. So the classifier is trained on the embeddings, and then we query by just sending the embeddings. Okay? So let's see first the standard quantization. This is projection and quantization. And also compare with just quantizing the raw signal, actually down to 1 bit, which is the rate here. If you know, Hog features give you, I think, 35 or 36 dimensional embedding, you can quantize it down to 1 bit, and you get this performance here, this point. But then you can use quantized Johnson-Lindenstrauss embeddings, and using 1 bit, 2 bits, and so on, and for different bit rates, get different performance. But you can see that here the optimal quantization is down to 1 bit again. Okay. Now this is not the rule. Remember, in the standard quantized Johnson-Lindenstrauss embedding, I told you there are all these constants that we need to figure out. But anyway, if you do that, you can get a 47% improvement at the bit rate for the same probability of error, the same matching accuracy. But you gain another thing. You gain flexibility in your design. If you want to trade off the probability of error for a lower bit rate, you can actually do that. You can operate in these points here. Okay, this is not something that you can do by standard scalar quantization of the actual features. You have to do to vector quantization and so on, which is much more difficult. And then you can do universal embeddings, and you can actually do a slightly better improvement. So this is what you see here. The green curve is, not the green, the whatever color is that, is the 1 bit embedding, and then with universal embeddings, you can get a slightly better improvement. That's not very impressive, but you can still get a slight improvement in this case. Another experiment we did is in the Zurich buildings database. This is another database commonly used in image retrieval. It's 1,005 images, so there are 201 buildings, 5 viewpoints per building, and we used 4 pictures of the building as a database, and 1 picture of the building as a query image. And we extract SIFT features. We do the embedding. And then we query the database. We do the same thing in the database. We extract features. And then we query the database using nearest neighbors. So this is, again, the results with standard Johnson-Lindenstrauss embeddings and quantization. If you do 1 bit quantization, that's as a number of measurements, as a number of projections. 1 bit quantization, 2 bit, and so on, up to basically unquantized. You can expect performance to improve. But again, this uses 20 bits. This uses 40 bits. Sorry, this uses 60 bits. So if you actually do it in terms of the rate and plot your curves in terms of the rate, you see that in this case, the optimal quantization is around 3 to 4 bits. And there is kind of they have very similar performance. 3 to 4 bits, 1 bit actually is very coarse quantization, but a lot of measurements. You improve by going to 2 bits. But then once you get to 3 to 4 bits, you get better quantization, but then you don't get enough measurements to preserve distances. Okay? So you can get a 33% improvement from the state of the art in this area. And you can actually show that if you naively quantize SIFT, if you naively send SIFT, you can get a 12 times improvement. If you quantize and naively encode SIFT, you can get a 5 times improvement. And if you were to just transmit the image, you can get a 23 times improvement in the rate. Now, if now you use universal embeddings, you actually get a much better performance. And the reason is that you get that you can actually tune your embedding to only preserve the radius of the signals you care about to recognize the nearest neighbor. So you can get a 33% improvement over the quantized Johnson-Lindenstrauss embeddings and a 50% improvement over the state of the art. So I'm almost out of time, so I'll go fast. There's one more aspect in this beyond image retrieval, which is that features reveal a lot of information. And in fact, we can provide some privacy guarantees. I won't get into that. The point is that if you embed things and you only preserve the distance of nearby things, if somebody wants to find more stuff, he cannot, because he doesn't have any more information. He only has nearby distances. And you can show an information theoretic guarantee that if signals are far apart, the embedding reveals nothing about their relationship. Okay, so wrapping up. Again, this is the main problem I wanted to solve. In fact, you know, I made this very specific G of a distance between x and y. And what I'm trying to argue here is that the embeddings are a very good tool for coding that preserves distances, which is very useful for inference. And they provide some kind of information scalable representation. The more distances you want, the more bits you use. It's actually very promising for big data and distributed systems. Incidentally, they do provide, that's what I mentioned yesterday in Snunstock, they do provide exponential accuracy, assuming you know how to reconstruct, which is a combinatorial problem. So really, they don't in practice. They're very efficient for coding and distributed coding, assuming you know how to reconstruct. There are some ways, but they're not as efficient. And they're privacy preserving. So with that, you can take any questions.
Time for one or two quick questions.
Laurent Jacques has some results recently on quantization.
Mm-hmm.
How does his result compare to the
So I think his results are slightly tighter. It doesn't change the experiments because it's the same method. I think his results on the quantized JL are slightly tighter, and they're a bit more recent than that. He's using the buffoon's needle to try to figure out where things will fall in that quantization interval. Yeah, so I think they're slightly tighter. Same order of constants, but same order of results, but probably slightly tighter in the constants.
Any more questions?
Yeah.
So one thing about the reconstruction guarantee, right?
Mhm.
You said that the coding algorithms are difficult, but when you have, is it that with high probability you can achieve exponential accuracy for every point?
So the guarantee is that if you can achieve consistent reconstruction, and that's where the combinatorial part is, and with extremely high probability on the draw of the matrix, then all the points get exponential accuracy.
Questions for Professor again? So we'll start again in 12 minutes.